screen, right?
Hi, everyone. Great. We are very pleased to have Anna Pelczar-Barwacz from Jagiellonian University, one of the oldest universities in the world that I just learned. And she's speaking on small operator ideals on the Schlumprecht and the Schreier spaces. Anna?
Thank you, Benjamin. Thank you very much for the invitation to the webinar, and it's a great pleasure to speak here. I want to say something about the results on the cardinality of small operator ideals on Schlumprecht, well, on certain space, Schlumprecht and Schreier space of a finite order. So this is a joint work with Antonis Manoussakis, and let me just put the basic notation, right? I recall the operator ideal as linear subspace, which is also a two-sided ideal. And I'll be interested in strictly singular operators. I recall it's just strictly singular operators such that it is not isomorphism on its image when restricted to some infinite dimensional subspace. And I recall also the notion of small and large operator ideal. It's useful to distinguish these classes with respect to the relation with the strictly singular operators. And again, I'm sure you're familiar with this more than I am, but I will recall just a few examples of first list of Banach spaces where we know when we don't understand completely the lattice of closed operator ideals are the classical examples. These are P and C0 spaces of on gamma, where gamma is infinite cardinal. Then we have the C0 and L1 sums of finite pieces of Hilbert spaces, and then the very recent result of sums of the spaces of those two types. And on the other hand, the spaces with exotic structure, right? The celebrated example of Argyros-Hayden, and the spaces built within the framework of the Argyros-Hayden construction, as well as the C of K, where K is the Koshmider's version of Morfka space. And on the other hand, of course, we have these beautiful examples of on large cardinality of closed operator ideals on Banach space. I think that almost all of them appeared in this year, if I'm not mistaken. The first one is the smallest cardinality, the uncountable chain of small ideas in L1 plus C0 and L1 plus an infinity. And then came the beautiful examples on the function spaces, and on Cyrilson space and Schreier space of finite order, with respect to in terms of large operator ideals, and also recent work of Daniel Freeman, Thomas Schlumprecht, and Andreas Jacques, giving a criterion for 2 to the continuum and small ideals, which works in all LP plus LQ apart from this first space on the list, and LP plus C0, of course, which I haven't wrote right here. We want to add to this list Schlumprecht space and Schreier's and some complementable resultant Schreier space of finite order, giving also a way of building continuum many ideals on Schreier space of finite order, but small ones. So what I will first give a very simple general criterion which we applied in case of Schlumprecht space. So the setting is we are on a Banach space, and we fix the normalized basic sequence there. We take the span of it and by orthogonal functionals. And then I'm considering only operators of a special form. In fact, the form is absolutely not special at all. Any operator going into Y, a space with a basis, will have such form. But the only important things are those marked with blue. I mean that there is a sequence which is semi-normalized in X, which is carried onto the basis of Y, right? So this is the only point which is important here. The form of the operator is easily attained, but the only point here is that we have a sequence which is carried to En, right? And the sequence is bounded. And when I will be thinking about the operator in this with the sequential form, I will be always attaching to it this fn's and xn's. Why? Because I'm interested in this following sequence of parameters, right? Which describe the behavior of the norm of the sum of functionals and the norm of the sum of the vectors. And we add here this epsilon because we don't assume unconditionality of the sequences of the basis. So those epsilons play for it. And so this kind of asymptotic behavior of the chosen sequences fn's and xn's. And obviously, I mean, straightforward, we have such relation between those two parameters, those sequences of parameters. And it is not hard to see that if I take operators which have a different behavior in terms of this condition, right? I mean, the functionals on R and the vectors on T behave differently, say. Then I can separate easily T from R. I want to separate not only T from R, but I want to separate T from the ideal generated by R. And this is why I add some new condition, which is very strong. I have the same space X, and Y is the same as on the previous slide. Remember, this is the span of some basic normalized sequence. And I'm considering operators which have this very strong supremum norm property. I mean, on the image of the unit ball via T, the topology of the supremum norm and of the norm inherited from X is the same, right? So this is a strong property. If we add, if X does not contain copies of C0, then of course any such operator must be strictly singular. But of course, on the other hand, if you have Y is just ENs or just the unit vector basis of C0, then you have this condition for free. And in such setting, I have the following theorem. If I take operator which is of the sequential form, and I take a family of operators which are of the sequential form, and additionally they satisfy the strong supremum norm property, and I know their behavior are different, right? Remember, this is the asymptotic behavior of the sums of k many elements of functions defining R, and this is an asymptotic behavior of norm of the k elements of vectors defining T. Then actually I can separate T from the operator ideal generated by the family B, right? And I'll give just a sketch of the proof, which is quite elementary. I take the objects as in the assertion, and then I assume that I don't have the separation of the desired form. Of course, I can require that the operator from the ideal is of this kind, of this form. And since T is taking each xn into n, I know that Q on xn is semi-normalized, so I can pick some subsequence on which this sequence is semi-normalized, and then I profit from the strong supremum norm property of R, right? So as this sequence is semi-normalized, it will be also on some further subsequence semi-normalized in the supremum norm. And I got this, right? So this is just straightforward. And then using some part of because up to this point, I haven't used this separation R from T in terms of the asymptotic behavior of the objects defining them. using, for example, this thing here, which follows from this condition, I can, passing to further subsequence, I can make sure that these functionals and these vectors form biorthogonal sequences. Of course, I don't need even this. It is enough to assume, for example, that xn's are weakly null. Nothing special in this. And then it is very easy to take the estimate relating the norm of the sum of xn's to the norm of the sum of the functionals. Just straightforward. And we arrive into the contradiction, because taking suitable sets of indices, we kill the relation assumed here. So the proof is quite elementary. We use it in the Schlumprecht space setting, and the whole work is in taking and in building operators which satisfy the assumptions. So this part of the proof is, as I said, straightforward, but the major work is on the choice of the Schlumprecht space objects. And I'm going to the Schlumprecht space. I don't want to give the precise definition. I will just only list the properties I will use in the proof, or which will give some information on the structure of the lattice of closed operator ideas on it. Well, Schlumprecht space, of course, is the famous example of the first arbitrarily distortable space, Banach space, and the starting point from the whole theory of powerful examples of Banach spaces with the algebra of bounded operators with tight control on the structure of it. So the Schlumprecht space is a reflexive space. Its canonical basis is unconditional and subsymmetric, which means equivalent to any of its subsequences. It is complementably minimal, and it follows that there is nothing between the ideal of strictly singular operators and the whole Banach algebra of bounded operators on the space. So if we are looking for the distinct operator ideas, we have to look for the strictly singular operators. And just from the definition of the space, it follows easily that the basis, this canonical basis I said at the beginning, is dominated by any block sequence in this space. And it is quite easy to see that it's quite, well, not hard to see that some properties of this block sequence xn ensure that the mapping xn to en is strictly singular. What is not easy is to prove that this mapping extends to the whole space, and that was done by George Androulakis and Thomas Schlumprecht. They proved that for some delicate choice of functionals, this operator of the sequential form is strictly singular and non-compact. In fact, it was proved that on the Gowers-Murray space, the first hereditary indecomposable space, there is an operator which is strictly singular, non-compact, but one of the middle point of the construction was going via Schlumprecht space. So what we did is that we play with this construction. This construction is very delicate. It involves taking repeated averages, using the definition of the norming set of Schlumprecht space, and it depends on the choice of the length of the averages. So very careful choice of parameters defining the length of the taken averages provides this property. If you play with the choice of these parameters, you are able to construct a family of small closed operator ideals on the Schlumprecht space, indexed by the subsets of reals, which means that you have two to the continuum distinct closed operator ideals, anti-chain of maximal cardinality and chain of maximal cardinality. And what we do in the proof we construct a countable family of functionals and vectors, vectors semi-normalized, indexed by a dyadic tree, so that if you go along one branch of the tree, then the functionals and vectors picked by this branch generate an operator of this Andronikis-Schlumprecht form. You need some estimates, some further, well, a lot of technicalities from the paper of Andronikis and Schlumprecht, from some estimates we have with Antonis in other paper on the strictly singular operator on Serelson type spaces. Here ENs, so the role of Y is played by the whole space. And if you take any two distinct branches of this tree, then the behavior of functionals of T given by one branch and vectors of T given by the other branch is as we need for the criterion. And it doesn't matter how these branches are related to each other. I mean, this is we don't pay attention to order here. And then we can easily define the family of small closed operator ideals of the desired structure, right, and of the desired cardinality. So for any subset of branches of this dyadic tree, I define the ideal indexed by this family to be the closed operator ideal generated by all the operators given by the branches in the family, and this gives us the result. What about the Schreier spaces? Well, here the situation is much different. The first Schreier space was defined, I think it was the first, in fact, space, a counterexample, right? I mean, this first space created to be a counterexample to a certain conjecture in 34, if I remember correctly, and the generalized Schreier spaces given by the Schreier families indexed by the countable ordinals were defined by Dale, Alsbach, and Spiros-Arges 92. Again, I don't want to give the definition, but just the properties. Of course, well, if I take n equals 0, then I get only C0. But for n greater than 1, well, the space has a shrinking unconditional basis, but it is not subsymmetric. And in fact, I have the following theorem, which we need for our result, that if some subsequence of the elements of the basis dominates other subsequence, then the sets of indices of the dominating sequence must dominate in a certain way the other one sequence of indices. And this is, I mean, this based on the Yanis Gasparis and Denny Long theorem, I mean, very requiring and very deep result. I will use it. I will need it later. We know that by result of Kevin, Tomek, and Niels that there are continuing many maximal operator ideals on the Schreier space for any n integer. And in order to try to apply the criterion I was talking about, we need some sort of C0 type behavior, which we easily get because, in this case, because any Schreier space is saturated with C0. Moreover, we have a ready form of operators which will be of the desired form. I mean, those are kind of sequential type of operators, and in my definition from the beginning of the talk, and the range is C0, so I have for free this strong supremum norm property I require. So what I do in the Schlumprecht space case, this En spanning Y was the basis of the whole space. In this case, I take it to be the sequence which is equivalent to the basis of C0. And I'm taking the operators indexed by infinite subsequence of integers. For a fixed j, a subsequence of integers, tj is just operator which carries the whole space via projection to the subspace spanned by a subsequence of the bases chosen by j, and then carries elements of the subsequence indexed by j to the basis of y, so to the basis of C0 in fact, right? So repeating the result of Kevin, Tomek, and Niels, we have that this is strictly singular. The one problem is that we cannot apply just easily the criterion from the beginning we applied in Schlumprecht space, because it is easy to see that we cannot separate those for two sequences I and j. We cannot separate them by the behavior of the norm of sums of functionals and norms of sum of vectors defining the operators. But still we can do something. And if we take infinite I and j, sets of integers, and we require that j are much bigger, say, than I, then we can separate this operator ti from the ideal generated by tj. And in fact we can do better. In fact, we can separate. We can have the theorem is valid also in case when the operator ideal is generated by a family of tj's, where each j with respect to I satisfies this condition, right? So the point here is not that I'm taking only one operator, ideal generated by one operator and not the whole family. The point is that I cannot really apply the criterion straightforward. And Benjamin, how much time do I have now?
I still have a lot. We only did.
Okay. If you permit me, I'll get back to the sketch of the general criterion from the beginning. So I'm going back here. Okay. If we repeat the reasoning here in the setting of Schreier space, up to this point, we don't use this condition, which is not satisfied, in fact, in our case. All these conditions are true. Also, we can go as far as here, because instead of this condition here, we can use just the fact that the basis of the Schreier space is weakly null. And in Schreier space, we can derive a contradiction from this point. We repeat the proof as here, but with a very delicate choice of this subsequence f prime and taking from M, profiting from some special properties of Schreier spaces. I don't want to go to the much of technicalities here, but we can pass to some infinite M prime with this property, which is not so very sparse, right? And then, if I arrive in the case of Schreier space to such situation where I have functionals given by the subsequence j and vectors given by subsequence I by orthogonal, then I apply the result of Ioannis, Gasparis, Daniel Long with corollary of Burton-Lawson, obtaining some relation between j's and i's. I do it very delicately, and then I arrive to contradiction with the choice, with the assumption on j and i's. So in case of Schreier space, I use only half of the criterion. I don't need this separation by the norms of sums of functionals and norms of sums of vectors, but just I use the fact that I can separate the operators by the unboundedness of the operator carrying subsequence defined by I to subsequence defined by J. This is very roughly speaking, because there's a lot of in between choosing the subsequence of subsequence which is desired in the proof. However, it can be done. This condition is not that symmetric as we manage in the case of Schlumprecht space. So we manage only to get the chain of cardinality continuum of small closed operator ideals on the Schreier space. So again, the question, in fact, asked in the paper of Daniel Freeman, Thomas Schlumprecht, and Andreas Jacques was, well, what is on the Schreier space? Do we have really only continuum many distinct closed operator ideals? Remember, there are only they show Kevin, Tomek, and Niels showed that there are continuum large closed operator ideals. We have that there are continuum many small closed operator ideals. The question is maybe we can obtain that at all we have continuum many closed operator ideals. And just as a byproduct of the reasoning we have here, we obtain something about the structure of the operator as ideals in the Schreier space, answering a question of again Kevin, Tomek, and Niels Lawson. We obtained that not all strictly singular operators on Schreier space factors through C0. And how we do it? Well, remember, we know that the operator carrying the Schreier space, nth Schreier space to C0 is strictly singular for n at least one. We can show that the operator carrying xsn to xsn minus 1 is also strictly singular, and we are able to find in the nth Schreier space a basic sequence which is equivalent to the basis of Sn minus 1. And it is easy to show that the space cannot factor through C0, again using some properties that this operator is not factoring through C0, again using some properties of Schreier space. If I can go back a little bit to this general criterion here, well, I want to point out this idea behind this reasoning here is very similar to the idea, from what I understand, the idea of the general criterion of Daniel Freeman, Thomas Schlumprecht, and Andreas Jacques, in a way that we identify some geometric properties of operators which separate operators, and add some supremum norm behavior which allows for passing from separating operator from operator to separating operator from the ideal generated by the family of operators. However, in our case, the technical conditions which allows for separating operators from themselves are incomparable. We have a very simple condition here, and it works in different setting for different cases. However, well, the idea is similar. Right. I think this is all I wanted to say. I hope not too technical. Thank you very much for your attention.
Oh, thanks so much, Anna.
Thank you very much.
It's pretty quick, so it's only 30 minutes. So that means we can have a lot of discussions and a lot of questions. So
sorry, maybe I will. Yeah. Maybe I was going too fast, so I'm sorry if I can.
That's fine. So we're like school kids now. We can go home earlier. So any questions or comments? I mean, we have enough time to ask you to give the talk again.
Oh, maybe I was still speaking, unfortunately, as usual.
People didn't get it, so we can. All right, Kevin, what's your question?
Oh, I don't have a question. I was just touching my hair.
All right, okay.
Yeah.
So this seems like one of the outstanding problems is the Schreier space, right? And whether or not there's uncountably many operator ideals on Schreier space. And it's known, if the space doesn't have an unconditional basis, that there is, if you don't assume unconditional basis, that there is a operator ideal. Excuse me. There's a space whose space of operator ideals has countably many, but for unconditional, it's not known. I'm just restating, right? That's the idea. Yeah. Example.
Mm-hmm.
Okay.
Sorry. Anya, can you go back to the first slide where you have all the list of the results?
Well, this is not whole list, right? I mean, I picked only some of them.
Okay,
small list. There's a lot of. This is the well. I'm not sure if you're saying about the big cardinalities or this complete description.
Yeah, this was just to have a look at this.
Yeah. I mean, and this is not complete, right? I mean, this general criterion works for also of Daniel Freeman, Thomas Schlumprecht, and Andreas Jacques works also for other kind of spaces, right? And well, we have the Mankiewicz space would continue many small ideas. Well, it would continue many closed ideals. So yeah, this is not all.
Are you aware of anything about quasi-Banach spaces? I mean, do the question make any sense, for example, for LP spaces for p smaller than 1?
Well, I haven't thought about it. Well, I don't know.
Can I ask something about what Kevin asked or said before? I didn't completely understand. I think it's not known if there is a space with exactly countably many different ideals. Is that correct?
There is an example.
There is an
example?
Yeah.
What is it?
Tomic has to keep reminding me of it. I think he sent me 3 emails reminding me of this example, but it's Matthew Tarbird. He has a space with a Kalkin algebra as L1, and this gives countably many.
No, this is, I think, finitely many. Only.
Yeah, he has spaces. Yeah.
But countably, not finitely. Not.
Yeah.
Real
countably, yeah.
This is stated as an open problem in.
No, not countably many. I'm afraid. Continuum many.
No. I continue. No.
A continuum, but not to the continuum.
I'm asking whether there is a space with infinite countably, exactly infinite countably many closed idea, different closed idea. Is there one? I think this is an open statement.
Are you sure? Tomic, did I misunderstand? I thought the Tarbird space had countably many.
No, this is just the Wiener algebra, so it has uncountably many maximal ideals.
Okay, so I'm definitely confused. My fault. Yeah. Okay, so I need 4 emails at least. Yeah.
So the Schreier space may be an example.
Well, it's quite easy to see. It has continuum many. Yeah. Just identify them with holomorphic functions and take point evaluations on the.
The Tarbird example was exactly finite limit, right? So
I must have. I didn't understand. I'm sorry about that.
But can I just say, if you break what I think Thomas Schlumprecht calls the Texan rule, if you allow non-separable spaces, then it's easy to get an arbitrary I mean, any cardinality of the closed ideals, because I think if we look at the Matt Dawes or the Kramsluft-Dawes result there, then you basically take your set gamma of a suitable uncountable cardinality, and that will do the job for you.
Even you get exactly. So what's the structure? Is it like a chain, or what is?
Yes, they're well ordered. So I think if you want countably many, I think you would want to take gamma to be something like Aleph omega. Is that right, Tomek?
Yeah, absolutely. Yes. The point is that it's hard to get it with a separable Banach space.
Oh, definitely, yes. As I say, I'm going outside the, I'm breaking what, as I say, Thomas calls the Texan rule that all Banach spaces are separable and probably should have a basis, right?
Yeah, thanks for clarifying. I had it backwards.
So one can ask questions like sort of like spreading model structures. You know, you put a partial order there. Are there any forbidden structures in the closed ideals? Like when you look at it as a partial order set in terms of inclusions, does anybody know any sort of forbidden configurations? Like, or one configuration implies, you know, like uncountable or something like that.
You always have a unique smallest element, because you will have the closure of the finite ranks. So
right.
You start with 0 and then you go like one step up.
Minimum, right? Okay. And I think the maximal doesn't exist, right? So that was Valentine, right?
Sorry, what maximal?
I guess it depends on the chain, right? I mean, just in terms of inclusions, right? If you just look at as like a partial order set.
Largest element, I believe, doesn't exist.
Sorry, what were you saying?
I'm just trying to understand if there are any sort of pattern. If you look at it in terms of inclusion, like as a partial ordered set, like what do you always get, or what you
Well, a lattice. You get a lattice, but apart from that, I think you cannot say more.
Okay. Well, for example, in the case of spreading model structures, if you have like a countable chain, then you get uncountable chain. So that implies something like that. So are there any sort of structures like that anyone seen in this lattice? That doesn't seem to be there. I mean, this is related to Guidon's question, right? If you get exactly countably many for the separable, maybe it's not possible. I don't know. Okay, so I'm going to stop recording here. Anna, thank you so much, but we can, of course, continue our discussion.